Alex Adams, and this is my presentation on optimizing the placement of radar observing materials on military aircraft by computer simulation. As of 2022, the U.S. Air Force has 1,017 F-16s in service, which makes up over 20% of all active aircraft in the U.S. Air Force. And the F-16 is a multi-role combat fighter jet developed for the U.S. Air Force in the late 1970s. And the F-16 also has a larger radar cross-section compared to other newer fifth-generation aircraft. Recently, military radar systems have become so advanced so that they are able to detect and shoot down advanced aircraft such as the F-16, F-22, and F-35. According to defense officials, Russia's new S-500 missile defense system has the capability to shoot down the F-35 and F-22, which means they can also shoot down the F-16. Fighter pilots, due to the nature of their missions, have a higher probability of incidents, accidents, and fatalities occurring. Now, for those who don't know, radar works by sending out radio waves. These radio waves would hit an object and bounce back. This bounce back wave is all referred to as the bounce back wave. And the bounce back wave relays information such as the object's size, speed, and shape. There are two types of radar, active and passive, but my study focuses on active radar. To the image to your right, you can see that the radar sends out an active wave and it hits an object, and this wave bounces back and that relays to the radar various information such as the object's speed, shape, size, etc. Now, for those who don't know, radar cross-section is a measure of how detectable an object is by radar. A larger radar cross-section means this object is more detectable and vice versa. Radar cross-section less than 0.1 meters squared is considered stealth. Now, radar cross-sections of an object can be modified using different techniques. One of these techniques is radar observing materials. Radar observing materials are effective in reducing the radar cross-section of an object due to the material's unique properties. Materials such as iron oxides and titanium composites are used for radar observing material applications. One common example of a radar observing material being iron ball paint, which was seen used on the F-117 Nighthawk. Now, Feko software is a 3D electromagnetic simulator that simulates the effect of radar on arbitrary shapes. It was developed by Altair Engineering. Now, three studies that use radar cross-section and radar observing materials also used Feko software, and it was proved reliable in a study on radar cross-section reduction using characteristic mode analysis, analysis of radar cross-section reduction of fighter aircraft by means of computer simulation, and radar cross-section analysis of unmanned combat aerial vehicles using Feko software. Now, the question my research aims to answer is where is the best place to put radar observing materials on the surface of military fighter jet aircraft in order to reduce the radar cross-section without applying it to the entire aircraft. Now, the goal of my research is to determine the optimal placement configuration of radar observing materials on military aircraft by placing RAM in different arrangements on three different 3D models of multi-role military fighter jet aircraft, such as the F-16, F-15, and F-18, using computer simulation software. My mentor's role in this research was to provide guidance and resources throughout the entire process of the study remotely as they live on the West Coast, and my role in this research was to identify the project scope and goal and to perform all mechanics of study and data analysis. The materials I used was my laptop to run all simulations below. HyperWorks was used to convert the 3D model of the aircraft into a .ig's format. CAD FICO was used to make the different fighter jet scenarios, and Altair Knowledge Studio and PostFICO was used to compile, compare, and visualize the data gathered. To obtain my 3D models, they were all obtained through publicly available CAD libraries. The models were then imported into the HyperWorks software, where they would be converted to a .ig's file for the FICO software. Otherwise, it would not be compatible for that software. As you can see below, these are images of the fighter aircraft in the FICO software. To test the aircraft models, I used four scenarios under a frequency of 11.1 gigahertz, and for each simulation, the radar cross-section was recorded. In the first scenario, the entire aircraft was covered in radar observing materials except for the canopy and radome surface. In the second scenario, it was entirely covered except for the canopy, radome surface, turbine, and exhaust. In the third scenario, the aircraft was entirely covered except for the parts not covered in scenario 2 and the air inlet of the fighter. In the fourth and last scenario, it was covered only on the horizontal and vertical stabilizers and the wings. In the first phase of my project, when I initially tried to collect data, it did not work for various reasons. For the first reason is that two different methods were used, RLGO and MOM, and these stands for ray launching, geometrical optics, and method of moments. These are two different methods that can be used to gain the radar cross-section of an object in FICO software, but they yielded two different results, so my data was not consistent. Additionally, there are modeling issues with the aircraft as seen in the screenshot below. which caused the software to not be able to run. And there were software issues when I did run it, as you can see in the two other screenshots provided in the phase one section. Another issue that I faced in the phase one of my project is that I was using the student version of the Feko software. So some of the limitations that I encountered with the student version of the Feko software is that there's a limited restricted model size for the student version, which didn't allow for complex and large simulations. Additionally, it came with a limited range of frequencies that you could simulate, whereas the full version offered a broader frequency spectrum. And additionally, there is limited post processing capabilities, which didn't allow me to access advanced visualization tools or features for the data analysis part of my project. How I overcame this issue is that I contacted Altair and asked them for access to the full version of the FICO software, and they were more than happy to oblige. And this is how I overcame most of the challenges that I faced in the phase one of my project, and which allowed me to progress to the phase two of my project. For phase two, I was able to collect my data, and the greatest radar cross-section reduction varied for each plane, excluding the first scenario. Scenario 4 had little effect on reducing the radar cross-section of any of the planes. The third scenario saw the greatest reduction on the F-16, which is seen in the black graph, and it also yielded reductions for the F-18 and F-15. Scenario 2 saw the greatest reduction in radar cross-section for the F-16, which was seen in the green graph, but it also yielded significant radar cross-section reduction for the F-18, which is seen in the red graph. And the spikes in the radar cross sections for all of the three graphs listed there are due to protrusions on the aircraft itself, such as its wings, stabilizers, etc. Now, conclusions that were drawn from my research is that each scenario recorded a drop in radar cross section, but the most significant drop was recorded in scenario 1 due to the fact that the entire aircraft was covered, so the total radar cross section would decrease substantially. But the greatest drop was not consistent with the other three scenarios. And the radar cross section drop of all for this entire research was not low enough to be considered stealth, but the drop in radar cross section still makes the fighter difficult to detect, which increases pilot survivability. Scenario 4 is impractical and effective for each aircraft due to the fact that it reduces the radar cross section by small margins. The wings and stabilizers still had radar cross section spikes despite being coated with radar observed material, which could be due to the fact that dihedral corners often yield high radar cross section values, and this could be further studied in different studies. Scenario 3 is ideal for the F-16, as it took the singular air inlet on the fighter into account and reduced the radar cross section by the greatest extent, excluding the first scenario. Scenario 2 would be ideal for the F-15, as it takes into account the dual exhaust on the rear end of the aircraft, and it would not hinder engine efficiency, as there's no ram on the actual turbine of the engine. Scenario 1 saw the greatest reduction for all aircraft, but this was the expected outcome. Theoretically, it would be the best application, but it may face some issues realistically. Additionally, various factors must be tested before this is applied to the real world, as the cost of radar observed materials may deter policymakers from the first scenario, and additionally, weather conditions could hinder the effectiveness of radar observed materials on reducing radar cross section. And unfortunately for me, I cannot include these factors into the actual simulation software. For future opens up opportunities for future studies because it explores artificial radar cross section modification of objects without altering its shape. It explores the use of computers in simulating aspects of vehicle design. This research is also useful in both public and military sectors. It also opens up studies on the effects of vehicle shape on radar cross-section modification, as shape proved to be the main factor for the experiment outcome, and it's also considered a major design element of aircraft. For the software side of things, it is ideal to use a single solver method for any future studies, and it is also ideal to add a comparable value for the research question, such as cost, weight, etc., and to use a single solver method, either go with RLGO or MOM. Here are my references, and thank you for listening to my presentation.